Good morning. So we can start. So I'm Alexei from IMPA, and it's my great pleasure to introduce Professor Gigliola Staffilani from MIT. So Gigliola graduated from University of Bologna and then earned a PhD degree in 1995 from the University of Chicago, continuing with the postdoctoral studies at the Institute of Advanced Studies. So then Professor Staffilani worked in Stanford University, Brown University, and now she holds the position of the Abbey Rockefeller Mose Professor of Mathematics at the Massachusetts Institute of Technology, MIT. So then Professor Staffilani was elected as a fellow of the American Mathematical Society, of the American Academy of Arts and Sciences, then at the National Academy of Sciences, well, and so on. So that's just a little part of what I found. And so her research concerns harmonic analysis and partial differential equations. So today Professor Gigliola Staffilani will talk about the study of wave turbulence, a meeting ground for mathematical techniques. So we're very happy that you came with the lecture, please.
So first, can you hear me? I would like to thank the organizers for the invitation. I've never been in Brazil, so this was a wonderful occasion. And then I would like to thank all of you for staying here on Friday morning. I know this was a very intense week. I have been here for the whole week, and it was great to see so many young people. Well, I'd like to thank also whoever supported my research. Hope NSF keeps going. Not clear at this point. But let me just represent with this picture what I'm going to say today is a tiny, tiny little tip of an iceberg. And then in terms of wave turbulence, there has been an incredible amount of work in all sorts of branch, I wouldn't say just of mathematics, but of science in general. So I like to start talks with pictures. Pictures say more than words. So let me just say that this is a collection that might seem strange to you. What's the common denominator about all these pictures? Well, the common denominator in general are waves. In fact, wave turbulence, as I will say in the next slides, try to give you a little bit of a definition of it, deals with interaction of waves of all sorts of dimensions and scaling in a way. So I wanted to give you a sense of the type of phenomenon that involve waves. Of course, this is just an example. The first one you see is a very, very small scale. This is a picture of a Bose-Einstein condensate. I will go to that again in a little bit. This is much more familiar to everybody here. There's just coffee, and when you try to mix it, there is some kind of turbulence going around, and certain waves at different scales, like our scale. I love to think about this picture here. This is the one about freak waves. In fact, within wave turbulence, we like to study what are the common phenomenon, but also what are the rare phenomenon. Freak waves is an example of a rare phenomenon. And you understand already from here that you're going to have to introduce some kind of probability within the studies. And then this one was a very famous picture that came out a few years ago, the first recognition of interaction of waves that are dealing with gravity. Now, the next ones, I like this one because one of the type of equations that we're studying within wave turbulence are dispersive equations. And these are equations, and I will give you an example, the most typical one, which is the Schrödinger equation, that has the property that if you don't put any boundary data, the wave is going to continue and it's going to, if there is no boundary in fact, it's going to have the amplitude shrink to 0. This is kind of interesting because if the system is isolated, there is conservation of energy, so having the amplitude shrink to 0, it's kind of counterintuitive, but that's one phenomenon that happens for the dispersive one. And of course, the idea of the rainbow, I like it because often when we have to study very complicated signals, what we like to do is think of them as a sum of simple ones. So the light, in fact, is the superposition of much simpler waves, sine and cosine, different amplitude, and so on. And then we become much more technical. These are pictures that show up in our papers. This is one that describes cascade from high scale to low scale. And then you will see these other ones later on, so I'm going to stick to that just to give you an idea. So I went from the more physical one up on the top to the bottom, which is things that you see in math papers. Now, the wave phenomena, as I say, it's the subject of this talk in particular. And in principle, you can say, well, if you want to start looking at a wave phenomenon, they come from particles, so why not just studying the trajectories of each particles and just see what happens? In principle, you can do that with the physical laws that we have either from Newtonian physics or quantum physics, whatever. And why don't we do that? Well, for two main reasons. One is because understanding what happens to a single particle and reconstruct the wave and so on, it will not tell us a big picture. So what the actual phenomenon does as a whole. But also because, simply speaking, if you just think of the particles in a glass of water, there are 10 to the 24 particles in there. And so the system that you will need to study is incredibly huge. And that's not efficient and neither interesting. Since I mentioned in my title wave turbulence, let me give you at least an idea what it is. There is not precise definition, of course. And I'm part of a collaboration among physicists and mathematicians and pure and applied, supported by the Simon Foundation. And in our web page, this is what we decide to put as the definition of wave turbulence. So given a physical system with a large number of waves, when they are present, the description of each wave is not that interesting, just like the description of each particle is not that interesting. What's important is what becomes of physical importance is the practical use of the density, the statistics, basically what we can say of the phenomena as a whole, not as a single wave in this case. So in this lecture, I will encounter some of the mathematical tools that we have been using in order to study this part, I will say, a very small fraction of what we call wave turbulence theory. By the way, if people have questions, don't hesitate to stop me. Now, it turned out that at least in the pure math side, lots of different fields of mathematics have come together in the study of wave turbulence. Now, some are kind of expected, such as, for example, Fourier harmonic analysis. I mentioned before, when you study a complicated wave signal, you wanted to split it into signals that you recognize and you understand better, and then you interact them. The phenomena that I study are nonlinear, so this interaction becomes complex. And Fourier harmonic analysis are really strong fields that can understand how to reconstruct from simple to complicated. Then another thing that's kind of, dynamical system, fluid dynamics. I'll show you the picture of the water, the coffee with milk. I think less obvious is, for example, graph theory. How does that come in, perhaps? Or even more unusual, it would be analytic number theory. How is that combined with what we do here? I guess Svetlana, when she gave her talk, and she also started from a model from physics, she ended up at some point talking about numbers that are Diophantine or Liouville and going into number theory. You will see this will happen also in this talk. Okay, I didn't put here much more stuff, such as the numerical experimentation, also the physical experimentation in the wave tanks. I leave that to the physicists and experimentalists. This is more what we see in pure math. Now, the first example that I wanted to give you on how we go from particles to wave, a description of that, perhaps, is corresponding to the first picture that was in my slide. That's the Bose-Einstein condensate. So what is that? Well, let me describe very briefly with this cartoon here, thanks to the Wikipedia. I bought that from the web. So let's assume that you have a tank with very diluted gas or bosons, and you wanted to understand what's the property of this gas when the temperature goes to absolute zero. This is very different than what happens when you keep the temperature, and if people know, you derive the Boltzmann equations. That happens at basically this temperature. This is a different phenomenon. You're going to absolute zero, and we move from the Newtonian physics of the particle and the Boltzmann derivation to quantum physics. So in order to describe what happens when we lower this temperature, it's much better to think of the particles not as a particle itself, but a little wave packet. And at the beginning, when the temperature is not that low, the proportion between the distance of the little wave packet and the wavelength is not comparable. Then as you lower the temperature, that becomes comparable, and all these different wave packets, in this picture, by the way, here, this comes from Scientific American, and there was a picture that was on the magazine to celebrate the discovery in laboratory of Bose-Einstein condensate in the 90s. So all these little guys, think of them as being wave packet, if you want. And as the temperature lowers, they lose completely their independence, and they coalesce together into this blob here. And that's the wave, also called a giant matter wave. OK, this is the physics. I'm not a physicist, so this is as much as I'm going to tell you. But from the mathematical point of view, what do mathematicians do? How do you describe going from this situation, lowering the temperature, and picking up all these different kind of phenomena that happens at the different kind of scales? Well, mathematically, and this is, I'm hiding everything. Remember the iceberg with a tiny little dot on the top? That's what I'm doing here. There's a lot behind it. But mathematically, what happens is that these wave packets, of course, they are put together and they are coalescing somehow, and the dynamics at that time is given by some kind of Hamiltonian. I'm not going to write anything, but it can be described. This is the many-body system, and it's also there is a hierarchy of equations depending on the number of wave packets that you have, which is called BBGKY hierarchy. And you can either take the temperature, go to zero, or you can rearrange or rewrite the problem so that you let the wave packets number n goes to infinity. And when you do that, you get Gross-Petaviersky hierarchy. I'm not writing what that is, but what I want you to think about is that this hierarchy here, it's connected with the Schrödinger equation. Now, thankfully, Marco yesterday gave a talk, and he talked about the Schrödinger equation. So you already have an idea of what's supposed to be. And by the way, in this process here of doing this, there is a lot of work of many, many mathematicians. And in 3 dimension, for example, around 2007, there is the fabulous work of Erdős, Xiao, Schlein. OK, so we got to the Schrödinger equation. So let me parse for you what that is. I'm going to give you, I'm going to describe for you what that is. So U, it's our wave. In fact, U is a function that takes space, time into complex numbers. And the equation tells you to do the following. Take an I, that's the I from complex number. And then you take a partial derivative t. You take 2 derivatives in all directions. That's the Laplacian. And this is the linear part of the problem. And then there is a nonlinear interaction. The most common one is the cubic NLS. So it's the absolute value of U squared times U. And then there is this lambda, which is a constant in front. I renormalized everything. And what's important about lambda is its sign, plus or minus. And I will go back to that in a second. And in this problem, we are assigning the initial data. So I'm telling you, I'm giving you the picture how this wave looks at time 0. And through the rest of this talk, I'm going to assume that your space variable is in a donut, in a torus. And you say, why? I mean, you know, why are you not done it? Well, this is just telling you that I'm considering periodic boundary conditions. So this is periodic problem in space, and the period along the different directions might be different. We'll go back to that in a second, but let me just express that this is all I'm going to do in this talk. Now, I just want to point out that assuming that you have boundary conditions that are periodic versus assuming no boundary conditions at all, like you are in all RD, makes the problem much harder. And this is sort of related to the fact that I mentioned before what dispersion is. Like if you don't have boundary condition, the waves is free to move to infinity and the amplitude becomes 0, it disperses. But once you put boundary conditions, you have both the nonlinear activity, but also the interaction of the wave with the boundary, bouncing back, how it's bouncing back, all that makes the problem difficult, more difficult, at least intuitively, and mathematically definitely more. Now, since this comes from physics, we have at least two conservation laws. So there is the mass, which is, you can think of it as the L2 norm square of u, and then the Hamiltonian, which is given by the kinetic part, that's the gradient, one derivative in all directions, and then the potential part, that's potential power 4, because we are looking at the cubic NLS. The lambda comes back here again, and now you understand why the sign is important. If it were negative, there is a competition between kinetic and potential, and the Hamiltonian energy could be negative, and in that case, you might have blow up. But if lambda is positive, which is what I'm going to consider throughout the talk, then there is no competition, and the Hamiltonian being conserved and the mass being conserved together will give you that the H1 norm, the Sobolev norm H1, is uniformly bounded in time, and that maintains a nice dynamical, constraint. Now, let me go back to, what's the solution of the problem? Well, I mentioned to you that the natural norm for this space, if we want to use the mass and the Hamiltonian, is H1, right? So just one derivative in L2 and the function itself in L2. Now, if I'm looking at this problem as is written here, and I'm taking it at face value, I'm supposed to take two derivatives. And that brings me outside the physical space in which I would like to be. So we're going to reformulate what we mean for solution. As you know, there are many different, when you do PDE, there are many different ways of saying that something is a solution of an equation. It could be in the classical sense, really take two derivatives and whatever. That tells you that you have to take a lot of derivatives. Or it could be in the weak sense. So in this case, what I call a solution is the following. By the Duhamel principle, you can connect this initial value problem with this integral equation, where u is equal the linear part. So this, what I call STOU0 is the solution of this linear problem. Same initial data, but set equals 0, the nonlinearity. So for now on, this is my notation for the linear solution. But then you had to account for the nonlinear part, and this is the integral. There's some constant here, which I forgot. But anyway, 0 to t, and then the same group acting on the nonlinearity. Now, you understand that saying that u is equal to something which has u in it, tells me nothing. But it tells you what could be a method to prove that there is a solution. In fact, for me, finding a solution of this could be finding, for example, a fixed point of this operator here on the right. If I assume this to be an operator for whatever space, I didn't tell you what space, but if this operator has a fixed point, then I solve the problem. So that's the sense in which I look for the solutions. Now, another way of thinking about fixed point is also defining a sequence and finding a limit of that sequence in the following sense. So I wanted to solve this identity. So now I'm thinking, let me find a sequence that converges, and then automatically, if that sequence converges, this part will go to the limit. This one is just constant, does not depend on n, and this part will go to the limit, and then I will get my solution. So how do I find this sequence? Well, I could think of the first element of the sequence to be the linear problem, the linear solution. You can write it explicitly. I'll give you the formula in a moment. Then the second one, the second element, is the linear plus one. In the non-homogeneous term, I'm going to plug in, instead of u, I'm going to plug in the step before, which is this. And then you keep going. At step n, you have the linear plus the non-homogeneous with the un minus 1. Now, if you're lucky enough that you understand this sequence, and then you find that there is a limit, then that's your solution. But you understand that this is not as simple as I said, because first of all, I don't know in which space this sequence has a limit. I don't know if the limit is unique, depends on the space, right? But it tells me that, something that I will need to resolve is understanding, just even from the first, we call this the first iterate, the product of linear solutions. That's the starting point. I need to understand, for example, that this part of my sequence behaves well, as it will behave at least as well as the linear part. Otherwise, I cannot do anything. So now, with this principle, I understand that I need to figure out what's the product of linear solutions. We have sort of two options. The first one is periodic Strickard's estimates. I'm going to tell you exactly what they are. This is a purely deterministic approach. There is no probability whatsoever. I take the product of linear solution and I figure out in which space they live. And this kind of periodic Strickard's estimate, periodic because I'm in the periodic setting, of course, you can be also in RD. It's limited in the sense that you can do these estimates, but there are going to be some counterexamples if you go at a linear, regularity which is too low. But if you manage to do this periodic Strickard's estimate, then your statement, when you look for solution, will sound something like, for all initial profile with this regularity, I have a unique solution and so on. There is another way, which is more recent. Both of them, by the way, in the periodic setting are due to Bourgain. It's based on large deviation type estimates. This is more of a probabilistic approach and allows you to basically sift through the counterexample that you have for the Strickard's estimates. So you're able to lower the regularity of your initial data. You can have initial data which are less regular. But then, of course, the statement will sound differently. You will be able to say, for a set of probability 1 of initial data, you get solution uniqueness and so on. So I'm not going to say much about this, but I want to say something about that. OK, so what are these Strickard's estimates? Well, like I said, I'm interested in understanding the product of linear solution. Another way of thinking about it, if you think of Q to be a natural number, you are looking at the LQ of this number. So if your Q is 4, for example, like I wrote in the particular example that I want to work at, you have the product of 4 linear solutions. And which Q you need in order to resolve the problem very much depends on what's the nonlinearity of the problem and so on. But that's the general idea, is figuring out in which LQ, both time and space, this linear solution lives. And so the typical estimate that you want is the LQ norm, space, time, has to be bounded by the initial data, so the LQ norm of my linear solution, you want it to bound with the initial data with some derivative, the least that possible, of course. So for some s greater than 0. Now let me pinpoint a particular case. In the cubic NLS, in dimension 2, the relevant Q is going to be 4. Now, we know everything about the linear solution. We know it's a complete expression. In fact, the linear solution with initial data u0 takes the following form. It's the sum, so basically you take Fourier transform, you solve an ODE for each frequency, you got it, but it's the sum n and z2, because I'm in dimension 2. This is the Fourier coefficient initial data, and this what is the action of the Schrödinger group. It modulates by e to the I t the time, and then this should be, if I'm in a square torus, 2 pi, you will just see the magnitude of the vector n square. But as I mentioned, you can have different periods in different directions. So this alpha 1 and alpha 2, where positive, tells you which period you have. And then you reconstruct via your basis in L2. Now, it is important for what comes next to distinguish two different of periodic boundary conditions. The one where the ratio between alpha 1 and alpha 2 is a rational number, we call that rational torus, or the ratio between alpha 2 and alpha 1 and alpha 2 is an irrational number, we call that irrational torus. Now, if you were in RD, instead of a sum here, you will see an integral. That would be an oscillatory integral, and people had done streetcars estimate for a very long time, starting with streetcars, in fact, using oscillatory integrals, restriction of Fourier transform, and in particular, the reason why they could do that is because you could do integration by parts. But when you take periodic data, you have a sum here, and there is no integration by part that can help you. And this oscillatory sums is more the realm of analytic number theory. That's why psychologically, people were completely stuck until early 90s, when I started doing my PhD, and took Bourgain's work to actually solve this. So Bourgain considered the rational torus. So let's, for simplicity, think that we are 2 pi, 2 pi, so it's easy to think about it. And if you are in the rational torus, in particular 2 pi, 2 pi, you can think of this alpha 1 and alpha 2 to be just integers. And you note, and that's easy to see, that this expression is not just something periodic in space, but it's also periodic in time, if alpha 1 and alpha 2, or if you are in a rational torus. So using this, so by the way, because you are periodic also in time, then your streetcars estimate in time, it obviously cannot be in R, so you cannot do L4 in R because it's a periodic object. You just do the L4 on your periods. That's why for the time, I also have pi here. So the first thing that Bourgain used in the rational case, like I said, this is early 90s, was to realize a simple observation that this is periodic, and then basically you write it down the L4 as the product of two linear solutions in L2. You do Plancher L, you work in the Fourier world, you do a Holder estimate, and you pick up the measure of a certain set. What's that set? Is the measure of this set, so you had to measure the lattice points I dotted for you, these blue ones, that sit on this particular parabola. This parabola is very special because I'm in the rational case, so alpha 1, alpha 2, and R are all natural numbers. So geometrically, that's what you had to find, the number of lattice points on this ellipse. But in practice, the way you solve the problem, the way you count how many of these lattice points are in this set, is by using Gauss' lemma, which basically tells you how many solutions this Diophantine equation has. That's it. And for that, there was a very special perfect estimate that depended on the radius or the eccentricity of the ellipse, and it's this expression, but less than r to the epsilon. So Bourgain helped us on that, and analytic number theory basically informed some theorem that usually you find in harmonic analysis. Now, what about the irrational torus? Let me go back for a second. If you are an irrational torus, this is no longer something that you can solve with the Gauss lemma. And so for about 20 years, we were stuck. All the theorems that we knew about Well-Poisson, streetcars, and so on were all done for the rational case. And then was again Bourgain, so you see this 2014, with Demeter, and they proved exactly the same type of estimates, also for irrational tori. So at this point, this is the same estimate, in fact. You lose an epsilon derivative from that r to the epsilon. But the proof was completely different. In fact, there was no number theory whatsoever in here. And it is the corollary from the L2 decoupling theorem. It used to be an L2 decoupling conjecture, one of the biggest conjecture, I would say, after Kakeya, which, by the way, has been solved. As a corollary, this decoupling theorem, L2 decoupling theorem, you get the streetcars estimates. It's not a direct proof, but it's a corollary. And what came into this, the possibility of solving this, were some new concepts that were brought into harmonic analysis, in particular by my colleague Larry Guth, which incident geometry kind of estimates, but also the polynomial method. I'm not going to say more about this, but there is no number theory. In fact, well, I just wanted to advertise some work with my students and postdocs. Beside the Strickard's estimate, there was also a bilinear Strickard's estimate that we also used with the 2 decoupling. And even more sort of interesting but intuitively correct is when you do the Strickard's estimate in the rational case, the time interval in which you can do is dictated by the periodicity of your solution. But if you are in the irrational case, it's intuitive to think that if your torus is irrational, when your wave hits the boundary and the torus is irrational, the wave has a little bit more time to, doesn't really spread out as in the dispersive case, but has a little bit more time to live with the right estimates. And this was quantified in the longer time Strickard's estimate by Deng, Germain, and Goethe. But what it was maybe more surprising, but not so much, is that by using the techniques, purely harmonic analysis techniques, similar to the one of the L2 decoupling proof, Bourgain, Demeter, and Guth proved that theorem in number theory. In fact, they proved the Vinogradov mean value theorem, which consists in having a very sharp estimates of solutions of a certain system of Diophantine equation. So we are going in the opposite direction now from Bourgain's original work. Harmonic analysis is informing analytic number theory. There is this beautiful interaction between the two areas. Okay, now that we know that we can do Strickard's estimate for all boundary data, periodic, you should believe me that you can solve the existence, uniqueness, continuity with respect to the initial data. All of this goes under the definition of well-posedness for the Schrödinger equation. And I'm sticking here to dimension 2, but there are equivalent things in higher dimension. And independently of whether lambda is plus or minus 1, you can prove that there is a solution, at least for a small time, as long as you have s greater than 0 regularity. In fact, I want to say to the young people here, if you just tell me that the initial data is finite mass, the problem is still open. Even just local solution, we don't know. We cannot prove that. That's because the loss of the epsilon regularity. Anyway, but if lambda is 1, so you have this beautiful boundary, bounded estimate coming from the Hamiltonian and the mass, then we can iterate the local well-posedness because the time depends only on the energy and the mass, and we can get a global solution. So in principle, you can say that, in fact, you can say that there are global, unique solutions for smooth data for sure. We just need to be s greater or equal than 1. So then the next question that I wanted to address, now that we know that there is a global solution, what can we say about the evolution for a long time of this solution? For short time, we know that it's a small perturbation of the linear part. But what about long time? When do we actually start seeing kicking in the nonlinearity? All right, so in order to tell you what we do in this case, I need a definition. And this is a definition of energy spectrum. So for me today, energy spectrum is the following. You take your solution, which now we know it exists, at least for the problem I'm presenting. I'm taking the Fourier coefficient of that solution, and I'm going to take the magnitude of it and square it. Of course, as you change frequency, this change. And this whole set here, we call it sigma t, I define energy spectrum. And the question is, what is the dynamics of this sigma t? What happens to it when t goes to infinity, plus or minus infinity? And even would be even more interesting, can we find an equation that this sigma t satisfies? And then we can start the equation and maybe give some property. Okay, so let me start easier first. And let me start with the notion of transfer of energy. What do we mean? What do we mean with that? And this is related to the evolution of the spectrum. Oops, sorry. Let's assume that at time 0, this green thing, the graph green, should be discrete if k is, of course, an integer. But this green thing is my initial spectrum. That's what it represents. And then it evolves. And the question is whether this bump that is near small frequency is going to move to higher ones. Here I only described the K large, but should be also on the other side. So is there this motion from low frequency to high frequency? This is called either transfer of energy or forward cascade. Well, there is one thing that you should immediately notice. Remember that we have the mass conservation. And by Plancherel, if I take the area of the subgraph, that is exactly the mass. And since the mass is conserved, this transfer, if it exists from low frequency to high frequency, has to happen so that at all times the area of the subgraph is constant. So that's a pretty strong restriction how this stuff can happen. But there are other kind of restrictions that I will mention in a moment. But let me tell you approach one in trying to answer this question. And this, again, goes back to Bourgain. The approach one is the following. So we are interested in understanding what happens to this absolute value of u hat square. So the idea is, well, if there is a transfer to higher frequency, if I multiply by this weight to the s here, I think greater than 1, and then I sum everything, this quantity should grow because I have more weight on the k large. But then you recognize that this is nothing else than the hs norm square. So this is why people look at the limit as t goes plus and minus infinity of the hs norm square for s greater than 1. By the way, I didn't say this before, but pay attention that the Schrödinger equation is very different than the heat flow. You can go in both directions, and it's equivalent, time reversible. So lots of people have been working on this in trying to figure out what can we say about this limit. And here I just mentioned a few names. There are different approaches, PDE approach, computational approach, also dynamical system approach. And I'll give you some examples. Approach 2. This is based on finding the effective dynamics for the spectrum, something that I was mentioning before. In other words, trying to find an equation that this spectrum satisfies. I'm going to talk about this in the second part of the talk. But basically, you need to take your dispersive equation, that's in my case NLS. The lambda is going to go to 0. That's called weak nonlinearity. And then the size of my torus, let's think about square, is going to go to infinity. And then doing some gymnastics and introducing some probability in there, it does pop up effective equation for this sigma t, and we call that wave kinetic equation. So I'm going to go back to that. And these are some of the first people that, and this is actually important also in the study of climate and all sorts of other things. So let me concentrate on approach 1 first. Now, there are lots of constraints in this approach. I told you, for example, the fact that the mass is conserved, that area of the subgraph has to be constant, but other things that happens. So in dimension 1, the NLS, cubic NLS, and also KdV, I didn't write it down, but the cubic, they are so-called integrable system. They have infinitely many conserved quantities. And in fact, if you put together this conserved quantity, you have uniform bound of any HS norm. So there is no growth of the HS norm. Another situation in which this happens, which is not dimension 1, is the cubic NLS without boundary conditions. So if you live in R2, and a few years ago, Dodson proved that you have scattering for this global solution that we already knew existed. What that means is that as you let t goes to, let's say, plus infinity, you can find a profile U plus in HS, in HS. And if you evolve linearly this U plus, that approximates your nonlinear solution. So this is saying that at infinity, your nonlinear solution behaves like a linear one. And for the linear solution, the HS norm remains constant. So this tells you that with this simple triangle inequality, that for time very large, you sum and subtract, this becomes constant. This is smaller than epsilon if you're large enough, so you have a uniform bound. So there is no growth of Sobolev norm if you don't put boundary conditions. And finally, what do we know about the actual problem? So this is the situation in which we are periodic, we are not in dimension 1, we are in dimension 2, and we are nonlinear. Well, as for now, we don't have a sharp result, but different people, starting with Bourgain, Soinger, Planchon, and Vichiglia, proved this bound for the HS norm, t to the s minus 1 plus epsilon, in completely different ways. And since we don't think this is sharp, I will tell you in a second, but that's what we know so far. And if you are in the irrational torus, things are different, and I will mention in a moment. So in general, that's all we know here, and we believe we can sharpen that. This is, for any solution, there is a bound of this type. But then next question is, can I find an initial data that has an HS norm that grows, right? That's, so this bound from above and an example from below. Well, not yet. We only have partial result for the problem on the torus T2. And this is what we know, for example. So fixed T2, rational. It's very important that you think of rational. This is a constructive theorem. So we are in the torus of dimension to think about square, 2 pi. Fix you S, that's the order of derivative. Fix a small delta, and fix a large K. Then I can construct for you, this is a constructive proof, an initial data which is in your HS, that is small, less than delta. And if I wait long enough, capital T, the solution U at that time T becomes larger than fixed K. So that's what we know so far. Now, let me give you an idea. This is bringing me to the fact that there is some dynamical system here. In order to prove this theorem, I'm not going to tell the details, but what we did was start with, we take the solution U, we look in the Fourier world, we have an infinite dimension Hamiltonian system. It's way too complicated, non-linear, it's way too complicated to study that. We extract from it a toy model, which does not represent the whole thing yet, but just a sort of a subdynamics part. And this toy model lives on this complex sphere. This is due to the fact that it's a conservation of mass, and I renormalize to be 1. And the problem, you translate it into showing the following. On this toy model that lives on this sphere, there are large circles that are invariant. And you can order them. Basically, my order represents being low frequency to high frequency. And the end game will be to prove that if you start close to the first one, of course not on the first one because you keep rotating like that, but close to the first one, you avoid all these traps, and you get to the last one. And that's the forward cascade. So that's indeed what we do. And then there are people that know how to do dynamical system better than us, Guardia, Kaloshin, House, Procese, and so on, who refine this result to give us an idea how long does it take and so on. But this is to say that there is some dynamical system in there. Now, we do not know what happens after capital T. It might be that this norm that became large is going to become small again. We don't believe that, but that's something that we cannot rule out. And what we expect is that the growth should not be more than a log. What about in the irrational case? This was for the square, basically rational case. Well, with Bobby Wilson, we proved that this toy model construction absolutely cannot happen there. But this might still grow due to something else. And we thought that this was a dichotomy, like rational case, there is this kind of growth. Irrational case, that's not possible. But then Guardia, Giuliani and Guardia proved that, and this we are going to sort of what Svetlana a little bit was saying last time, if you are close to rational, and I'm not going to say more in what sense, in a number theoretical way, but if you can approximate your irrationality, your torus, with rational numbers, then you can use the result that I mentioned before and some kind of perturbation argument and translate it also for the irrational tori that are close to be rational. It's much more than this, their theorem, but that's the result. And now let me give you a peculiar result. So this is peculiar, mathematically speaking, but it's kind of a warning to people who decide to study physical phenomenon in a boundary domain by saying, okay, I'm going to assume periodic boundary data. Because these two results are opposite to each other. Okay? So it's about the same phenomenon, it gives opposite results. So let me parse the first one. Let's fix S greater than 1, that's the order of derivative. This is due to Hani, Posadeur, Tsetko, and Vishilia. I would like to have stayed just on the torus of dimension 2, but actually we don't know that because we cannot control a long-time dynamics. But take the torus and cross it with R. So your physical domain is now a cylinder. And they prove that the dynamics of the toy model is actually it's representing the dynamics of the whole NLS in this domain, though. And they prove that there is a solution U that has initial data small, but then later on, the HS norm on a fixed sequence of time becomes bigger than log. And the reason why this is peculiar is because with Nicola Camps, we proved that this was in the rational case. If you are very rational, okay, whatever that means, then this fact absolutely does not happen. And you know, things are rational and irrational, one tends with respect to each other, so you cannot make a tank of anything which is rational boundary condition versus irrational. So anyway, there is very nice math behind it. At the moment, we don't have a precise sharp result. We would like to say if you are a number of this type, we have one result. If you are the other type, you have another result. We are not quite there, but this is just to say that we are studying the same phenomenon, but in different tanks, let's say, and you get opposite results. Okay, now I want to spend 10 minutes, is okay? Maybe the next 10 minutes, maybe less, let's see, talking about the second approach, the one that we would like to give, in which we would like to give an equation, which solution is my spectral sigma t. Okay, so I'm going to give you the hand-wavy derivation of what we call the wave kinetic equation. Hand-wavy, not simple, but this is the argument that physicists already knew forever, and it goes in the following way. I start with my dispersive equation. Here I'm using the NLS just because we encountered the NLS from the beginning, but you can do with other kind of dispersive equation. And I'm looking at a weak nonlinearity. So I have an epsilon here that's going to go to 0. I'm putting myself in a boundary, in a condition in which I have a periodic boundary data, but it's a square or a cube if you want, hypercube. So it's the same period in all directions. Not having that will make things even harder. So let's ignore this. And I also assume that there is a background probability in this problem. If you don't have any probability, you cannot do this. That background probability is really on the distribution of the Fourier coefficient of the initial data. So that's what it is. I'm going to be more precise in a moment, but we assume that the initial distribution for U0 is given. And that's why you can talk about expectation. You have to rescale in the right way. Epsilon to the -2 in this context is, in terms of epsilon, it's called the kinetic time. So you're going to rescale. At this tau in general is very small, uniform constant but very small. And what you prove, or what you want to prove, is that as you let L go to infinity, so this box becomes basically R2 in this case, and then epsilon, the nonlinearity, goes to 0, the expectation of this spectrum here, energy spectrum that has been rescaled, which I'm going to call nk tau, satisfied an equation, this equation, which is called the wave kinetic equation. So how do we do this? I mean, there is a limit. L goes to infinity, epsilon goes to 0. And when you have limits, you have to be careful. And all you have is the distribution at time 0. And so you have to control what happens later on. So fundamental work on this has been done by many people, but the type of description I'm going to give you today, you can find it directly in the book of Nazarenko. And let me tell you a little bit how you get it, at least formally. Now, let's start with the NLS here, as I mentioned before, and let's do what I just said by rescaling the right way. And the Q that I mentioned before, if you're curious, is of this type. But don't worry about it. The only thing I want you to think about is that there is this delta function. So that means that K1 minus K2 plus K3 minus K is equals 0. This is four-wave interaction. And then this delta function says that k1, the absolute value 1 of k1 squared minus k2 plus and so on equals 0. It tells you that you are in the resonance set, what we call resonance set. And then the combination, the symmetric way of this phi, this is four-wave interaction. Anyway, it's not important, but I just wanted to give you an idea. So how do we find this? How do we prove that indeed this limit that I'm computing is that? Formally, it's not too complicated. You start with the AKT, which is your, the Fourier coefficient of your solution. And we assume that at time 0, this is the distribution of my initial data, are random phase amplitude fields. That means you write AK0 as in polar coordinates. You have a phase, you have an amplitude. They are respect certain kind of probability, and they are independent with respect to each other. Now, the goal is to write your solution in terms of this infinite sum, which expanded in terms of epsilon, which will go to 0. So what you have to find, it's an algorithm, you have to find all these coefficients. AK0, that's the first one, AK1, AK2, and so on and so forth. And well, we have an equation for it. So the obvious thing to do is take this expression, plug it in, and match the order of epsilon. There is not much to do here. And you do that, and it's explicit. So the first one, obviously, that's no surprise, is the initial data. That's it. The AK1, which is the coefficient of the epsilon to the 1, is an expression like this. It's explicit. I didn't want to bother you with that. But what I want you to remark is the associated Feynman diagram. So K splits in K1, K2, and K3. And I want to represent it this way. When you go to the next one, A2, it becomes more complicated. But these three kind of Feynman diagrams will start showing up. And now you can imagine you can do infinite of these guys, an infinite expansion. And what you have to do at the end is compute this expectation. So you have to multiply these two things. Now, here I stopped at epsilon squared. That's what the physicists do. And they ignore everything else that epsilon to the k greater than 2. And when you do this, you use the fact that you have independence. This is a random phase amplitude. And take the limit, and there it pops the equation. Very simple. So that's the formal argument. Now, when mathematicians have to do this, you have to do all the epsilon expansion, interact all the Feynman diagrams. And these are n factorial, and unless you find some cancellation, you're completely doomed. So let me tell you what has been done in the strategic way. So we start with the work Erdős-Yau, Erdős-Almhofer, and Yau. In their case, it's not the nonlinear Schrödinger. It's actually linear with the random potential. They go beyond epsilon to the minus 2. And they, in fact, there is beautiful notes from Erdős and about diffusion, how you find diffusion and so on. Felipe Hernandez, in his thesis a couple of years ago, advanced this argument with a completely different paradigm, I would say. And Loccarin and Spon were the first one to consider the cubic, so the nonlinear NLS, but their distribution is via the Gibbs measure, which is invariant in time. So the distribution at time 0 remains constant later on in time. So that's something very helpful, and they proved the linearized wave kinetic equation. And then later on, Buckmaster, Germain, Hani, Chata start looking at this problem again in the fully nonlinear case. You see here a bunch of results until Deng and Hani, they completed the proof. And then I want to mention some work that I did with Binh Tran. But in this case, it's not the NLS. It's actually a KdV type equation. And some student of UNESCO also, this what we call ZK equation, but had to add a little bit of dissipation. Anyway, let me just summarize what are the tools that we use here. Probability, obviously, that's the distribution at time 0. Dispersive estimates, kind of like a streetcars that I mentioned before. Combinatorics is incredibly important. Graph theory, you have all these Feynman diagrams, and you have to classify them somehow and match them in a way that kills the factorial. Harmonic and Fourier analysis, that's always there, and of course intuition from physics. So I'm going to conclude by this quote that I like very much from Kolmogorov, which is obviously a giant in wave turbulence theory. And he said, mathematics is vast. One person is unable to study all its branches. In this sense, specialization is inevitable. I mean, all the graduate students here know. I mean, you have a couple of years in which you can do a bunch of stuff, but then if you don't focus, you don't get the thesis. But at the same time, mathematics is a united science. More and more links appear between its areas, sometimes in a most unexpected way. In fact, I think I gave you an idea how number theory comes in something that deals with waves. Some areas serve as tools for others. Therefore, an isolation of mathematicians into narrow borders should be destructive for our science. And I'm going to stop here. Thank you.